Hello. So yes, my talk is anything you can do. Anything you can do, I can do worse with macro rules. As the name suggests, we're going to be doing a lot of macro stuff. If you're interested in checking out these slides, they are published on GitHub and GitLab. I'll show a link to those at the end. If you'd like to contact me about those, well, it's there, and also my Discord there at the bottom. So, just a quick refresher. So, a few quick things. The first one is that at something is no special syntax. It's something I invented. It's a convention from very early days of Rust. It just is a little tag to let someone know what's going on in that rule. We also use recursion a lot in macros. You'll see that macros call themselves a lot, and that's because an individual rule itself cannot be recursive, ambiguous, or violate Rust parsing ambiguity rules. So what do we mean by a rule cannot be recursive? Well, rules only have rejects like repetition specifiers, so question mark, star, and plus. Those don't give you the tools for recursion. And a rule can't be ambiguous. Well, a rule can only be applied in one way to a particular input. For example, this rule here is ambiguous on the input baz. That token could match to either foo or bar, so we would get a compile error in that regard. We also cannot violate Rust parsing ambiguity rules, such as you can't have unpaired parentheses, square brackets, or curly braces. And you also can only have certain types of tokens come after certain types of token specifiers, so that Rust knows exactly what token a certain thing is part of. Like a comma can unambiguously follow a type, but maybe it can't unambiguously follow something else. And that whole thing is follow set ambiguity. The Rust book has the Rust reference has the full list of the restrictions in that regard. So with all that said, it's time for macros, but I'm sorry, the text looks a little funny on here. That's not how I remember it looking. The letters are wrong. Let's zoom in quick. They're lumpy. What? Huh? That's right, it's crime time, not just macro time. We're gonna do terrible, terrible things. It's not snack time yet. We're doing awful stuff. We're gonna define traits with XML and declarative macros. So, start of the evil arc. We're gonna take this trait here, right, with all these terrible metasyntactic variable names, right, and turn it into this XML. And if you'll notice in the little right-hand corner, we've got Ferris telling us to take a sip of our water. And if you're asking why would you do this to us? Excellent question, not gonna answer it. The better question is, how does it work? Well, let's look at a really small example. So this is just an example invocation, right? We've got a trait, name, foo, public visibility, and it's gonna be unsafe. And it's just invoked with the trait XML macro. So we're gonna run through this like genuinely one step of expansion at a time, so we can see roughly how you can take a really weird syntax like XML and turn it into something Rust understands. So my general approach to this is we take weird syntax and turn it into a tree of token trees, and then turn that into Rust. Also, I'm going to be using some line highlighting to highlight the important stuff, and red text shows what's going to be removed in the next expansion. So the first order of business, we expand to the actual parsing macro. We have the parse inner rule, and then the trait is the thing we're gonna look for at first, and that's gonna go away. And now we're gonna start looking for the tag pairs that define important things about a trait, like inner functions, inner types, inner constants, visibility, whether it's unsafe, so on and so forth. So the first one we see is names, so we're gonna grab that and jump to a name parsing macro. We can see here the important thing though is a callback. Macros cannot be passed as inputs to another macro because of out to inner expansion. If you have foo macro with an argument bar calling, then foo expands first before bar ever does. So if you want the output of bar as input to foo, you have to do a bit of recursion. You have to expand bar and then tell that to call foo at some point. So here we're calling sorry, let me turn on the laser pointer. There we go. We've got our name identifier macro. And then at some point in the future, we're going to jump back to the main parsing macro at this rule with these arguments. And that's how we can give input back. Anywho, we have the name foo now, and now we see the end name tag as well. And we've also got our name here. So we jump back to trade XML inner, and now we've got an extra thing at the bottom. We'll handle that and put it in the output just as a token tree. Easy enough. But we also now see visibility. And we go to a visibility parsing macro with the callback and our arguments. And notice how the callback also contains what we've parsed so far. We're keeping track of it as we keep recursing. This is all one big recursive tree so far. And then we've now got our visibility, parse again, and now it's in our output. We see unsafe, so we'll stick that in there. We see the end trait tag, and that's it. And now we're into the expansion part, now that we've got our tree of token trees. So then all of this is going to go into different parts of a trait definition. And then as we just step through, we'll get the name in there, we'll get the visibility in there, we'll get the unsafe there. And then finally, now that the output buffer here is empty, it expands. This does actually work for all XML. In the repository, if you're interested at all in checking it out, you can define anything you would in a Rust trait normally, except for meta items. I didn't feel like doing it. It was a lot of work. So why? There's a few points I'm trying to make here. Declarative macros are actually capable of a whole lot. Like XML to Rust is a pretty big transformation. And you also don't always need a procedural macro. This will allow you to simplify your projects because you don't need another crate with probably at least 2 necessary dependencies, sin and quote. And not having that will also reduce compile times a lot of the time, so long as your macros aren't really, really big. In any case, so let's get into a review of macro rules. First of all, why macros? Metaprogramming is an extraordinarily useful thing to have in a language. Like one of the really, really basic things is repeating lots of similar but not quite identical things. Like say you want to implement a 0 trait on a whole bunch of numbers. Well, you could write that out by hand, 3 lines apiece, no problem. Or you could have a macro, you just pass in your types and a default value, and there you go. In like 5 or 10 lines, you've got all the definitions you need. But then you can also define almost entirely new grammars that get expanded into valid Rust. They're also great for confusing people, including yourself, but don't worry about that part too much. So what is a macro rules? Declarative macros are kind of like functions on the abstract syntax tree. They're also the only kind of macro we'll talk about in this presentation. Procedural macros have a lot of resources out there. The point of this presentation was that there's not a whole lot for declarative macros. In one, we try to match on certain patterns or rules against a syntax tree input. The rules are tried in order from top to bottom. That's the arbiter between rules that might be able to be applied ambiguously. Both of these two rules here, foo and bar and foo next token tree, match the input foo bar, but which one actually ends up being used by the compiler depends on the order that they're defined in within the macro rules. So what are our abstract syntax tree node types or fragment specifiers? We have all of these. We've got items, blocks, statements, pattern parameters, patterns, expressions, types, identifiers, paths, token trees, my beloved, meta, lifetime, visibility, and literals. Each of these, except for token tree, are subject to regular Rust parsing rules. We also have the rejects like repetitions with the parentheses, $, and then the repetition specifier afterwards. And there are, as I mentioned earlier, some restrictions on what can come after, and these are a couple examples here, like expression and statement can only be followed by =0, comma, or semicolon. Pattern parameter can only be followed by =0, comma, equals bar, if, or in, and then there's a bunch more. And they will restrict very much what you can put after something. And to avoid this, you can use recursion, of course, or you can redefine your input format. So before we get into the actual patterns that I'm going to talk about, I'd like to mention something called fragment specifier composition. This is the idea that you can take multiple fragment specifiers, for instance, an identifier and expression, and turn them into one new fragment for example, a statement. But you can't do the opposite. An identifier and an expression can become a statement, but you can't break that apart again. That statement is now going to match as exactly one token forevermore in the future until you finish expansion. Token tree is really, really flexible for these operations, so if you can stick to it, I would recommend it. So here's just to reinforce the point, you cannot reverse it. We've got this me reaping macro. We're going to take in 4 token trees, and that's going to call me reaping again with match statement, and we're going to try to turn those 4 tokens into one statement. Me sowing is going to do the opposite. We're going to take in one statement and call me reaping to try to get 4 tokens out of it. And, well, if it works, that would be great. However, we're going to get this compile error that when we call me reaping in the me sowing macro, then we're only seeing 1 token getting matched. We didn't have anything to match this left-hand side token tree. So just there's one exception to this we'll talk about. However, just as a general rule, you cannot break apart tokens. And there's no magic, I promise. The 2 main restrictions of macros are that you can't have significant white space. That's it. Like, you can't do Python and declarative macros, I'm really sorry. Or YAML. And you also can't match tokens that are variables. So you can't conditionally do something if 2 tokens that are not literally written out by you in the rule definition are the same. You can match like foo equal some literal thing or the opposite way, but you can't have 2 unknown tokens on either side. Both of these are doable with procedural macros, but again, those aren't the topic of today's talk. So the main useful patterns, there are 6. The first one is recursion, because of course macros can call themselves. Internal rules. These are branches that you generally don't want users to call, but they're useful for you to do some manipulation of your current input. Incremental token tree munchers, which will grab chunks off the front of your list of inputs, and then you'll recurse with the rest. Push down accumulation, which will hold a list of tokens for you to expand later. Token tree bundling, which is just more or less you take a bunch of tokens, put them into a single list, and match it as one token tree. And callbacks, which is a workaround to let you pass the expansion of one macro as input to another. Just the asterisk there is the outward to inward expansion that I mentioned earlier. So really it's not passing a value, it's more like you recurse and now you give it something that you have just processed. So a couple disclaimers before we get into the details on each of those. You're going to hear and see, you've already seen this in the presentation a lot, the patterns are really, really hard to separate, especially because recursion is the basis for the other 5, and these patterns will also, in combination, let you parse just about everything, but don't, because they're the building block. For big inputs, you might just need a massive recursion limit, which may be a problem. It also may be a problem it takes a while to compile, or that you need a lot of memory. So declarative macros are also pretty difficult to debug, I'm not going to lie and tell you otherwise. And maintenance of them, especially for the XML one, 7,000 lines of declarative macros, let me tell you. All that said, these patterns can be leveraged to simplify some things for you quite a lot. And this talk is mostly going to be about some pretty cursed stuff, but I'll help give you some ways to make things easier on yourself at the end of the talk by debugging them. It'll make it a little more manageable, but it's not really debugging, sorry. So first, recursion. You've already seen this. This is the main tool that every other pattern uses to work. So we just have some macro that calls itself again, or another macro, but this is the easiest example. In function-like syntax, we roughly get an input, AST, output an AST, and we match on the input, call itself again. Easy enough. Then internal rules. Again, we've already seen these 2 slides prior. As I said previously, you won't generally want users calling these. They're used as helpers for you, the developer, to help grab new kinds of tokens or specify a certain mode of parsing, something along those lines. So here's an example. We've got some macro with an internal rule and then maybe some other rules, and it'll just expand to something. Not all internal rules have to start with @ something. As far as I'm aware, this started prior to Rust 1.0, where it was just You used at something to denote an internal rule just as like a helper thing, like you give yourself a function name, except actually it's a rule in a macro. And they're really useful for a couple things. First, you avoid polluting the crate namespace. Each rule in a macro could be its own other macro. You could have one rule per macro, but if you ever export even one of them from the crate, every other macro that gets called also has to be exported, which can be a problem with now you've got, oh no, now I've got 20 macros in my crate namespace. Whoopsies. They can also be used to set modes, which is helpful for setting a context. So if you run into the issue of follow set ambiguity, now you can just keep recursing in a mode of gathering tokens for, say, a path. And then once you reach the end of the path, now you can turn that list into one and go back to doing whatever you were doing before. So, incremental token tree munchers. You haven't seen this one yet. With these, you typically look to grab an expected pattern off the front. So you'll have a base case and a recursive case. And say with this example here, we look for nothing. And then on the other one, we try to grab the first one, do something with the first one, and then expand with the rest. That is the whole pattern of an incremental token tree muncher. It just might be a little more complicated for this recursive case. As a function, this example up here looks roughly like if we take an input AST, give an AST. If the input is empty, we expand to something. Otherwise, we recurse with we do something with the first one and recurse with the rest. Then push down accumulation. This one also hasn't been shown. The purpose of this is that macros have to expand to a complete syntax element. So if you're trying to build up a trait definition, when the macro is done expanding, you have to have a valid trait there. If it doesn't do that, then you're going to get a compile error and not the no tokens expected the rule kind. They allow, by doing push down accumulation, you can accumulate some stuff in intermediate expansions and then eventually form a complete syntax element. In the XML parsing macros, this was used to circumvent follow set ambiguity restrictions and also hold the parse tokens that were translated to the token tree format and then later expand. Then token tree bundling. This is the special case to fragment specifier composition being irreversible. We can actually do this. You take a bunch of tokens, stick them in a square bracketed list, and now you can match it as a single token tree. For example, in this bundle and unbundle, we take an identifier, type an expression, call it again, and now in square brackets, and it matches as a single token tree. Then we can print it out, quote unquote, as a single token here, and then we can actually reverse this operation. It does function. It's a very useful thing. Callbacks. Very, very generally, a callback looks something like this. You'll have an identifier or a path more generally, and then a bunch of arguments, and then you treat this identifier or a path as a macro, call it as such, and pass it your arguments. For the XML parsing macros, it was used to allow for macro reuse, which is that first point right there. They're really, really great for that. But you have to have a consistent framework for it. If you don't, then you're going to have trouble with, oh, this macro needs to be called this way, but this one needs to be called some other way. But if you have a consistent one, you can also form a call stack and then recursively pass the expansion of one macro to another as input. These are great for reuse. Like, I cannot stress that enough. Like, for the XML, every time there's a name, it is parsed by one macro. Every time there's visibility, parsed by one macro. Every time there's a type, so on and so forth. I didn't have to keep redefining that parsing in one place, which led to fewer failure points and fewer maintenance points. So if you ever have a larger macro project, try and give yourself some callbacks and a good framework for calling those. And also, water. So, debugging. Well, that's the neat part. So, if you're outside of functions, like, how do you debug things? What do when no println? Or debug if you're fancy. Introducing your new best friend, const underscore, of type string with stringify, or concat stringify repeated. These are incredible. You can see some residue of this from when I was debugging my XML macros and writing the doc comments, where we're stringifying the output tokens so that I can steal some of them and copy paste them into doc comments because I'm lazy. But hey, Oro, my macro plane just doesn't work. I can't use const underscore. I'm getting no rules expected the token. Actually, yes, you can. You didn't believe in your new best friend enough. So what we're going to do is write one rule that will take in literally everything. If you call the macro with nothing, this rule matches. If you call the macro with anything that doesn't otherwise get a compile error, this matches every single time. And then you concatenate with stringify all of those inputs so you can see as a string when you run cargo expand what input didn't match. Then granted, you now have to try and be the compiler and see why it didn't match something, but we're all clever here, right? So sometimes it's hard to figure out how a macro ended up expanding the way it did, but there's kind of a tool for that, which is a little bit useful, which is the unstable flag trace macros. When you run that, it'll go something like this with the bundle and unbundle macro that we had earlier. So when we call it, it'll say we are expanding this to, well, all that, and then it kind of keeps repeating until it reaches the end of the expansion. This is an okay tool, but if you have a really long recursion chain or a really complicated input, this is going to get unreadable very fast. So I would recommend instead trying to work with the const underscore method, as painful as that may be. Another thing you can do to keep no rules expected the token from coming up is just by, well, making rules that expect those tokens. I mean, it's pretty obvious, right? Like, hey, there's no problem. And my XML parsing macros do that a bunch as well. If you give them an invalid input, for instance, invalidly formatted XML, I have rules to catch that. As far as I'm aware, which is not very far, I'll give you that, there's no way to get no rules expected the token with my XML stuff. You will get a compile error instead telling you what went wrong, which is an incredibly useful thing for not just yourself when you're debugging something that's recursed like 300 layers deep, but also to users, so they can now get a message on, hey, this is what you messed up. This is what you should do to fix it. Because in your compile error, you can just concat and stringify a bunch to say, hey, I didn't expect this token. I wanted to see something else. Then a couple other brief things. This is just going to sound like general programming advice, but hey, use descriptive names for your rules, helper tokens, and fragments. Like, if you don't know what's going on, ooh, good luck when you come back to that in a few days. Don't worry about excessive complexity in a single rule either. That's not going to slow down your compile times very much. It's just fine. The problem is recursion, so try to keep that down if you can. But you don't need to be afraid of making other macros and making callbacks, especially if they can be reused in other places. That recursion is worth your time. And if you need more steps to finish parsing, add them. Nobody needs to see all the internal rules but you. Like for me, I could have halved the level of recursion in that top level XML macro by just combining the parsing and expansion steps, but that was too much work. I didn't like doing it. And the only people who saw it was, everyone watching this. Whoops. But yeah, that's all. The materials for this talk are available on my GitHub and GitLab at RustConf 2023. You are free to clone them. There's also a standalone version of this talk that's more meant to be referred back to instead of this video if you don't want to keep picking through it to find specific things. It has references to specific files and lines within them for examples, and also all of the code for the XML thing, and the other ones that are more instructive are in there as well. And thank you very much for your time.